Hello to all who are watching. My name is Ari, and today's video will be the first in a series where I will discuss integration techniques that, for one reason or another, appear to be lesser known or used by people. I have three main motivations for wanting to make this series. The first reason is that, from my own personal experience, when you handle integrals using only the techniques that were shown to us in a calculus class, especially if you've used them for a long time and nothing else, you can start to view integrals as unmeetable without them, which isn't true. Now, this doesn't mean that the techniques like U-Substitution, integration by parts, or partial fraction decomposition aren't useful. In fact, they are extremely useful and reliable, but they're not the only way. And if we allow ourselves to think outside the box sometimes, I think it'll help to make us more mathematically mature and flexible when tackling math problems, not just integrals, but math problems in general. The second reason is that, aside from the more abstract benefits that I just described, you might actually find some of the techniques that we're going to look at to be particularly handy or satisfying to use, and they could be a nice addition to your mathematical toolbox. The last reason is that I think it'll be a fun endeavor. I find a lot of enjoyment in playing around with math, and I hope through teaching I can make it fun for others as well. I would like to make one last remark before getting into today's technique. This video is going to be the first video of my YouTube channel, so if you have any comments, suggestions, or constructive criticisms, please feel free to post them in the comments below. My ultimate goal is to make this channel a fun and welcoming place to learn, and I would like to improve in any way I can to achieve this goal. The integration technique that we'll be learning today is called inverse function integration, or IFI for short. And this is an indefinite integration technique that's primarily used when you are given a definite or indefinite integral to evaluate. And you notice that the function that you need to find the antiderivative of inside the integral, or the integrand, has an inverse whose antiderivative is a lot easier to find. Now, that's a bit of a mouthful to say, so let's look at a more symbolic explanation. Suppose we have a function which I'll call f of x that we want to find the antiderivative of. Now, this could be for the purpose of directly evaluating an indefinite integral, but it could also be part of the process of evaluating a definite integral. In either case, we're going to need to evaluate this indefinite integral of f of x right here. Now, normally we could handle this with methods that we're already familiar with, such as U-Substitution, trigonometric substitution, integration by parts, etc. But depending on what f of x is, we might notice that it has an inverse function that could be much easier to find the antiderivative of. Now, the inverse of a function is typically denoted as the function with a -1 superscript. If it turns out that the inverse of f of x is easier to find the antiderivative of, if we could find some way or some formula for the indefinite integral of f of x in terms of the indefinite integral of its inverse, it would be extremely helpful. The big question at this point is, if such a formula that writes the indefinite integral of f of x in terms of the indefinite integral of the inverse of f of x exists, how do we find it? I will provide two proofs to find this formula. The first will be an informal visual proof to gain an intuition for the technique, and the second will be a more formal symbolic proof. In order to lead into these proofs, I'm going to lay out some initial assumptions on what kind of function we want f of x to be, based on what we have already stated. Because we want to find the antiderivative of f of x, it's only natural that we assume that f of x has an antiderivative defined. The way we're going to go about this is by invoking the fundamental theorem of calculus. This tells us that if a function is continuous on some closed interval a to b, it's guaranteed to have an antiderivative on that interval as well. So we're going to assume that f of x is continuous on a closed interval a to b, and therefore has an antiderivative on a to b. The vast majority of functions we encounter satisfy this condition, as it's highly likely that they have at least one closed interval that they're continuous on. The second assumption that we'll be making, due to the fact that we mentioned using the inverse function of f of x, is that f of x is actually able to be inverted. If we're going to call upon the inverse of f of x for the sake of anti-differentiation, it would likely be wise to assume that f of x is invertible on the same interval that we're indefinitely integrating, or in this case, the closed interval a to b that we assigned f of x to be continuous on. For our purposes, this assumption requires that every x value within the closed interval a to b outputs a unique f of x value. So no two f of x values can be the same within this interval. For your reading, I have written down a more complete description of what the function f needs to satisfy in order to be invertible over a to b. However, I will not go over it in its entirety to keep us from getting too lost in the weeds. However, there are two identities we should keep in mind for later that are in it, and that is that if g of x is the inverse of f of x, the inverse of f of x returns x for all x within a to b, and f of the inverse of f of y returns y, where y is any element in the interval f of a to f of b. Now, as it turns out, we don't actually have to make any more assumptions after this, because the last assumption that we would have had to make, namely that the inverse of f of x has an antiderivative, can be proved using the two assumptions that we have made. Using the assumptions that f of x is both continuous and invertible on the closed interval ab, it can be shown that f of x would have to be strictly monotonic on that interval as well, meaning that it is strictly increasing or decreasing. This can be proven using something called the intermediate value theorem, but it can actually be informally visualized why this is the case. Let's make the erroneous assumption that f of x does not have to be strictly monotonic on the interval ab, where it's also continuous and invertible. This means that on this interval, the function can be both increasing, can be some combination of increasing, decreasing, and staying constant. On this left graph, I drew a function that has parts where it's both increasing and decreasing. However, being both an increasing and decreasing and continuous function implies that the function has minima and maxima. And the presence of minima and maxima imply that there are points around these points where the function outputs the same value for different x values. And that's indicated by these three red dots that all have the same output value. However, the presence of these values is in contradiction with what we know to be part of the definition of being invertible on an interval, because to be invertible on an interval, the function in question cannot output the same value twice. And because of this contradiction, that means that f of x has to be strictly monotonic. Now, there is a case that I did not cover, and that's where the function could be constant over an interval. However, this will run into the same contradiction, because if a function is constant, it will have the same output value for multiple, or actually infinite, input values. So once again, this will lead to the contradiction with the definition of being invertible and imply that f of x has to be strictly monotonic. The right graph, we see a nice monotonic function. And because it is only strictly increasing in this case, it could be strictly decreasing. There are no minima and maxima. And if we draw this horizontal line to see all the different points where the function takes the same value, you'll see that there's only going to be one intersection. There's always going to be one intersection. Now that we have shown that f of x has to be strictly monotonic, it can be further shown that functions that are strictly monotonic and continuous on a closed interval, which f of x is, have a continuous inverse on that same interval. As a side note, although I am aware of this result, I have yet to work through the proof for it, so perhaps this could be an idea for a video in the future. We now know that f of x has a continuous inverse on the closed interval a to b, meaning that the inverse of f of x, which accepts any value in the closed interval f of a to f of b as input, will be continuous on that same interval. And because the inverse of f of x is continuous on this interval, it's guaranteed to have an antiderivative on that interval as well, due to the fundamental theorem of calculus as we discussed before. So what this tells us in total is that if f of x is a function that is continuous and invertible on a closed interval ab, f of x will have an antiderivative, was guaranteed to have an antiderivative on that closed interval ab, and its inverse, and the inverse of f of x is guaranteed to have an antiderivative on the interval that it accepts, f of a to f of b. And this gives us great hope that our quest to find a formula relating the antiderivative of f of x to the antiderivative of the inverse of f of x makes sense. With all these assumptions now said, we can finally jump into the first informal visual proof of the inverse function integration formula. To get started with this proof, we're going to be invoking the fundamental theorem of calculus again, but we're going to be utilizing a different formulation of it, which tells us that if a function is continuous on a closed interval, the antiderivatives that it has on this interval can actually be connected to definite integrals of the function on this interval. Because we defined f of x, the function that we want to find the antiderivative of using inverse function integration, to be continuous on a closed interval a to b, we can therefore connect the antiderivatives that f of x has on this interval to definite integrals of f of x on this interval. And from this point forward, we're going to denote an arbitrary antiderivative of f of x to be capital F of x. Now, the actual connection between an antiderivative of a function and a definite integral of a function on a closed interval where that function is continuous is given by this formula. And what this tells us is that the definite integral of that function from a constant, which we'll call c, to a variable, which we'll call x, where both c and x can take any value within the closed interval, gives us an antiderivative of that function on that interval. And when you change the constant c to a different value within that interval, it changes the antiderivative that it outputs. So, if we replace the arbitrary function that we've been talking about with the function that we want, which is f of x, and put it in the relationship, first, the f of x will become f of t because x is in the definite integral's bounds. So we're going to use t as a dummy variable. And the definite integral of f of t from the constant c to the variable x, where both c and x can be any value within the closed interval ab, this will produce an antiderivative of f of x in the closed interval ab, or capital F of x. It's worth noting that this relationship between definite integrals and the antiderivatives of the function that we're taking the definite integral of does not actually produce all possible antiderivatives that the function can have. It actually only produces a subsection of the antiderivatives possible. If we recall that antiderivatives only differ from each other by a constant, we can rectify this problem by adding a constant k to the end of the expression, where k can be any real number. And this allows, by varying k and c, us to produce, this allows capital F of x to represent every single possible antiderivative that f of x can have. The addition of this extra constant doesn't actually make much of a difference in the grand scheme of the proof, but I'll include it anyway for completeness. Because we have established a connection between the antiderivatives of f of x with definite integrals of f of x, we can start to visualize f of x's antiderivatives using the idea that definite integrals represent areas beneath a curve. In this graph, I have depicted f of x or f of t using the dummy variable as an arbitrarily chosen, strictly increasing, continuous, and invertible function on the closed interval a to b. We can see in this graph that the definite integral of f of t from the constant c to the variable x, where both c and x are always within the closed interval a to b, can be visually represented as this cyan area here, which is the area under the curve f of t from c to x. And I have this marked down as the cyan area. We can view this cyan area as one of three areas that, when added together, compose the total area of this rectangle right here, which has a base of length x and a height of length f of x. I have depicted these two other areas as the magenta area and the orange area. Now, the magenta area is just a rectangle itself with a base of length c and a height of length f of c. So this area, its area will just simply be c times f of c. The orange area, on the other hand, is a bit more of a conundrum, as it doesn't have a shape that we could easily find the area of, and it looks more like the area to the side of the curve f of t rather than the area under it like the cyan area is. We might still speculate that this orange area could be solved for as the area under some curve, but this curve would have to be produced by a different function other than f of t. Whatever this function is, we would have to take the definite integral of it from f of c to f of x, and this function would have to accept f of c and produce c as an output, and accept f of x and produce x as an output. This function, which takes the outputs of f of t as input and returns the inputs of f of t as output, sounds suspiciously like the inverse function of f of t. So our next logical step is to graph the inverse function of f of t and see what it tells us. But before we do that, let's finish writing down the relationship between the total area of this rectangle and its three component areas. So the total area is equal to the base times the height, which is x times f of x, and this will be equal to the magenta area, which is c times f of c, plus the cyan area, which is the definite integral of f of t from c to x, and the orange area, which we don't know yet. Now, if we solve for the cyan area and plug everything in, we'll receive that the definite integral of f of t from c to x is equal to x times f of x minus c times f of c minus the orange area. Now, let's see if we could find the orange area through the inverse function of f of t. By flipping the infinitely many inputs of f of t within the closed interval a to b along the t-axis in the first graph, with the y-axis in this graph, and by flipping the infinitely many outputs of f of t within the closed interval f of a to f of b along the y-axis in the first graph, with the t-axis in this graph, we receive the inverse function of f of t, which is shown right here. You may notice that the inverse of f of t is merely a reflection of f of t across the function y equals t in both graphs. And this isn't a coincidence, actually. It turns out that finding the inverse of a function is equivalent to reflecting it across the function y equals x or y equals t. By reflecting the areas across y equals t as well as f of t, we can see that the orange area is an area beneath the curve of the inverse of f of t and can hence be calculated by a definite integral of the inverse of f of t from t equals f of c to t equals f of x. We know this definite integral of the inverse of f of t is valid because we have shown previously that if f of t is continuous and invertible on a closed interval a to b, it has an inverse that is also continuous and therefore has an antiderivative on the closed interval f of a to f of b. With that said, we can finally replace the orange area in our equation with this expression, and from it, we obtain our first big result for inverse function integration. This result is what I like to call the definite form of inverse function integration, and what it tells us is that the definite integral of f of t from t equals c to t equals x equals x times f of x minus c times f of c minus the definite integral of the inverse of f of t from t equals f of c to t equals f of x. And f of x must be a continuous and invertible function on a closed interval a to b, and c and x must be values within a to b. The reason this formula is useful is that it allows us to calculate the definite integral of some function using the function outside of the definite integral and using the definite integral of the inverse of the function. So if we know how to calculate the definite integral of the inverse of the function, but not the definite integral of the function itself, this formula could be a useful workaround. All we need to do is set c and x to the bounds that we want. At the beginning of the video, I promised that we wouldn't just find a definite form for inverse function integration, but that we would also find a formula that writes the antiderivatives of f of x in terms of the antiderivatives of the inverse of f of x. Luckily, it won't actually take too much manipulation of the definite form of inverse function integration to receive that formula. All we need to do is recall from earlier that if a function is continuous on a closed interval a to b, the definite integral of that function from a constant c to a variable x plus another constant k where c and k can take any value within the closed interval a to b, and k can be any real number, this will output any one of the antiderivatives of that function on a to b. Knowing this, we can rewrite the definite integrals in the definite form of inverse function integration. Because f of x is continuous on the closed interval a to b, and c and x are within that interval, we can rewrite the definite integral of f of t from t equals c to t equals x as any one of the antiderivatives of f of x on a to b, which we call capital F of x, minus a real constant, which I'll call k of 1. Also, because the inverse of f of x is continuous on the closed interval f of a to f of b, and that f of c and f of x are within that interval, we can rewrite the definite integral of the inverse of f of t from t equals f of c to t equals f of x as any one of the antiderivatives of the inverse of f of x on f of a to f of b, which I'll denote as g of x, of f of x minus a real constant, which I'll call k2. If you are wondering why it's g of f of x instead of g of x right here, it is because in the definite integral, the upper bound is f of x instead of just x, as shown up here. Plugging these into the definite form of inverse function integration and solving for capital F of x, we receive that capital F of x is equal to x times f of x minus g of f of x plus this block of constants. This block of constants can be condensed into one constant, which I'll call c, where c can be any real number. Because capital F of x and g of x both represent antiderivatives of f of x and the inverse of f of x respectively, we can rewrite them in their indefinite integral forms. And this leads us to the second big result for inverse function integration, which I like to call the indefinite form of inverse function integration. This is the formula that I promised at the beginning of the video, relating the antiderivatives of f of x to the antiderivatives of the inverse of f of x. And specifically, this formula tells us that the indefinite integral of f of x is equal to x times f of x minus g of f of x, where g of x is the indefinite integral of the inverse of f of x. And it's important not to forget that f of x must be continuous and invertible on a closed interval a to b for this to work. And this constant c at the end is the constant of integration. Although we obtained the indefinite and definite form of inverse function integration using a rather informal visual proof, both of the formulations we have are actually correct. However, because the function we chose f of x to be does not encompass all the possible ways a continuous and invertible function can present itself, it leaves a little bit to be desired regarding the proof's rigor. For example, what if f of x was strictly decreasing instead of strictly increasing like we depicted? Or what if f of x didn't lie entirely or at all in the first quadrant? It might be useful to do a more formal proof to tie up these loose ends. However, because I've already told you that the results we received for the definite and indefinite form of inverse function integration are correct, we could probably omit a more formal proof, depending on how much one cares about rigor. With that said, I'm actually still going to run through a more formal symbolic proof for inverse function integration, because the proof that I have in mind draws a connection between some of the indefinite integration techniques that we're already familiar with and inverse function integration, which I think when we look at it will help us grow an even greater intuition for the technique. In order to start this proof, we're going to go back to the beginning and say that we want to evaluate the indefinite integral of f of x, where f of x is a function that is both continuous and invertible on a closed interval a to b. And this indefinite integral of f of x is valid on a to b because it's continuous there. And by the fundamental theorem of calculus, if a function is continuous on a closed interval, it has antiderivatives on that interval. Next, we're going to make a U-substitution by setting a equal to the inverse of f of u. This substitution is valid for x within the interval a to b and u within the interval f of a to f of b because we set f of x to be invertible on a to b. To complete the U-substitution, we're going to need to find the differential dx in terms of the differential du. And we know from how differentials are defined that the differential of d of x is going to be equal to the derivative of x with respect to u times du. Because we set x equal to the inverse of f of u, we can rewrite this as dx is equal to the derivative of the inverse of f of u with respect to u times du. Now, notice that this assumes that the inverse of f of x is differentiable on the interval f of a to f of b. This is an assumption that we didn't have to make during our informal visual proof that we did. It turns out from more complex proofs that other people have done that this assumption is not necessary. The inverse of f of x does not have to be differentiable. But for this particular proof that I'm doing, we do have to make this assumption to get to the end. However, at the end, we're going to drop this assumption because other people have proven it is not necessary. If we plug in our substitution x equals the inverse of f of u, and what we receive for d of x into the indefinite integral, we can see that it becomes the indefinite integral of f of the inverse of f of u times the derivative of the inverse of f of u with respect to u times du. And at this point, we can notice that this part right here equals u as one of the properties of inverse functions. So the indefinite integral will become u times the derivative of the inverse of f of u with respect to u du. We can then use integration by parts to rewrite this indefinite integral into a more tractable form. By letting v of u be a function that's equal to u and w of u be a function that, when differentiated with respect to u, equals the derivative of the inverse of f of u with respect to u, we can turn this indefinite integral, or equate it, to v of u times w of u minus the indefinite integral of the derivative of v of u with respect to u times w of u. Taking the derivative of v of u, we can see that it will equal 1. And taking the indefinite integral of dw du with respect to u, and discarding the constant of integration because it won't matter in the end, we can see that it will equal the inverse of f of u. Plugging these two results into here, we'll see that the indefinite integral of u times the derivative of the inverse of f of u with respect to u is equal to u times the inverse of f of u minus the indefinite integral of the inverse of f of u. By equating the indefinite integral of f of x with respect to x and the indefinite integral of u times the derivative of the inverse of f of u with respect to u, we'll obtain this equation right here. And we should remember that the indefinite integral of the inverse of f of u with respect to u is valid to say, because we know that if f of x is continuous and invertible on a closed interval a to b, we've shown that it will have a continuous inverse on f of a to f of b, and therefore have antiderivatives on that interval as well. If we let a function g of u be equal to any one of the inverse of f of u's antiderivatives on the closed interval f of a to f of b, we can replace this indefinite integral with g of u to produce this equation. We're also going to add a constant of integration to the end of this equation, c, because we were going to have to add it eventually to the end of this equation, and because we're nearing the end of the proof, we might as well add it now before we forget it. All we have to do now is invert the original U-substitution that we made at the beginning of the proof to solve for u, and plug it into this equation here. We know that we can invert this because if f of x is invertible on the closed interval a to b and produces an inverse that accepts any value in the closed interval f of a to f of b, then the inverse is invertible on its closed interval f of a to f of b to produce the original function f of x, which accepts any value within a to b. After inverting, u will be equal to f of x, and plugging this into this equation and using the properties of inverse functions to simplify the inverse of f of x to just be equal to x, we'll complete the proof and once again receive the indefinite form of inverse function integration, telling us that the indefinite integral of f of x with respect to x is equal to x times f of x minus g of f of x plus a constant of integration. And f of x must be continuous and invertible on a closed interval a to b, and g of x will be one of the antiderivatives produced by the indefinite integral of the inverse of f of x. Because we have now completed the more formal symbolic proof for the indefinite form of inverse function integration, we could continue on to see how the indefinite form can be manipulated into the definite form for inverse function integration. However, because I'm pretty sure at this point we're all pretty tired about hearing about proofs, I won't do it. But if you wish to do it on your own, I promise it is possible. With all these proofs said and done, we can finally get into what inverse function integration can do for us in practice and take a look at some examples. Now, you may be wondering at this point, because we just showed in our previous more formal symbolic proof that inverse function integration can be decomposed into a U-substitution followed by an application of integration by parts. What's so special about this technique? I mean, the title of my video is Lesser Known Integration Techniques, and here I've just told you that the first technique I'm covering can really just be viewed as a composition of two more common techniques. So, what's so lesser known about it? And my answer to this is that when you are given a definite or indefinite integral to evaluate, it can be remarkably difficult to spot that this particular U-substitution and application of integration by parts can produce the most efficient way of evaluating the integral. And because of that, in my own experience, it's better to view inverse function integration as its own separate technique rather than a combination of the more common ones. So when you're given a definite or indefinite integral to evaluate, you should take a quick look at the integrand, and if you suspect that it has a nice inverse, or it can be manipulated to have a nice inverse, you should directly apply the definite or indefinite inverse function integration formulas that we derived instead of going through the U-substitution and the integration by parts. Getting into our first example, we're going to warm up with a relatively simple indefinite integral, the indefinite integral of the natural log of x. Now, in a calculus class, this integral is usually used as a prime example of how integration by parts can be useful. So I'm going to first approach this in the more traditional manner using integration by parts, and then I'm going to show you how we can use inverse function integration instead to solve this. The integration by parts way of evaluating this integral is first by recognizing that natural log of x can be viewed as the product of natural log of x and 1. If we let u of x be equal to the natural log of x inside the integral, and the derivative of v of x with respect to x equal to the 1 inside the integral, then differentiating u of x with respect to x, we receive 1 over x because the derivative of natural log of x is 1 over x, and integrating this with respect to x, we receive that v of x is equal to x, excluding the constant of integration. And at this point, integration by parts tells us that this indefinite integral will be equal to natural log of x times x minus the integral of 1 over x times x with respect to x. Multiplying these two together and integrating with 1 with respect to x, which is just x, we receive that the indefinite integral of natural log of x with respect to x is equal to x times natural log of x minus x plus the constant of integration c. This indefinite integral is not too terrible to work through, and it can be handled perfectly well using integration by parts. However, let's take a look at what it would be like if we used inverse function integration instead. To start, let's recognize that the natural log of x has a domain from 0 to infinity, excluding 0. It's continuous and invertible on this domain, and its inverse on this domain is e to the power of x. Now, you might notice that this is not a closed interval, but that doesn't actually matter too much for using inverse function integration, because we could restrict this to a subinterval inside this interval and make this subinterval a closed interval. Let's call it a to b. And we could set a to be as close to 0 as we want, and b to be as large as we want. Now, when we use the indefinite form of inverse function integration, we'll see that the indefinite integral of the natural log of x with respect to x will be equal to x times the function inside the indefinite integral, which is natural log of x, so x times natural log of x, minus g of the function inside the integral, which is natural log of x again, plus a constant of integration c. Now, this g of x will be given by the indefinite integral of the inverse of the function inside the integral, which is e of x. So, and the indefinite integral of e of x is just e of x. So g of the natural log of x will be e to the power of natural log of x, and these functions are inverses of each other on this interval. So this will just produce x. So our final result is the same as what we received using integration by parts, and that's that the indefinite integral of natural log of x with respect to x is equal to x times natural log of x minus x plus the constant of integration c. We've now shown two different ways to evaluate this indefinite integral. However, in my opinion, both techniques seem to be of the same usefulness for evaluating this particular indefinite integral. So let's take a look at another indefinite integral that is perhaps more suited to be handled using inverse function integration. Here we have a more daunting integral, the indefinite integral of arcsecant of x over x squared with respect to x. As in the previous integral, I'm going to first evaluate it using more traditional integration techniques, and then I'm going to do it using inverse function integration. At the end, we'll then reflect upon which technique seems to be more appropriate. We are going to start this by using integration by parts. We're going to set u of x equal to arcsecant of x in the integral, and we're going to set the derivative of v of x with respect to x equal to 1 over x squared in the integral. Taking the derivative of u of x with respect to x, we see that it equals the derivative of arcsecant of x with respect to x, and taking the indefinite integral of the derivative of v of x with respect to x, we see that v of x is going to be equal to the indefinite integral of 1 over x squared with respect to x, which simply equals negative 1 over x. At this point, integration by parts tells us that the indefinite integral of arcsecant of x over x squared with respect to x will equal arcsecant of x times negative 1 over x, so right here, plus, because this negative sign and this negative sign will cancel out, plus the indefinite integral of 1 over x times the derivative of arcsecant of x with respect to x with respect to x. You've probably noticed that I never actually specified what the derivative of arcsecant of x with respect to x is actually equal to. Unless you're particularly knowledgeable about about identities of inverse trig functions, we'll have to calculate this on the fly. We can do this using implicit differentiation. If we set y equal to arcsecant of x and invert it, we'll get secant of y is equal to x. Taking the derivative of both sides with respect to x, we'll get secant of y times tangent of y times the derivative of y with respect to x is equal to 1. And then dividing both sides by secant of y times tangent of y, we'll get the derivative of y with respect to x is equal to 1 over secant of y times tangent of y. Now, recall that y we set equal to arcsecant of x. If we plug it back in, we'll get secant of arcsecant of x, which is just x, and tangent of arcsecant of x. We'll then need to figure out what tangent of arcsecant of x is. One way we could find tangent of arcsecant of x is by recalling that the inverse trig functions are functions that take the ratio between two sides of a right triangle and output an angle in that right triangle. Because we're working with arcsecant of x, let's recall what secant of x does. Secant of x is a function that takes in an angle and outputs the ratio between the hypotenuse of a right triangle and the side adjacent to the angle of the right triangle. Arcsecant of x, conversely, takes the ratio between the hypotenuse and the adjacent side and outputs the angle between them. We can therefore represent arcsecant of x as an angle in a right triangle, and the ratio that it needs to take in has to be equal to x. So we can satisfy this by having x be the hypotenuse and the adjacent side being 1. So x divided by 1 is equal to x, so the ratio is satisfied. Unfortunately, if we were to use this triangle to try to find what tangent of arcsecant of x is equal to, we would actually get the wrong answer. Although this right triangle does produce the correct ratio between the hypotenuse and the adjacent side to produce x, it's not accounting for a certain caveat that arcsecant and arccosecant have when drawing these diagrams. And that's that the way the trig functions are defined is that the hypotenuse must always be positive. However, arcsecant of x can accept x values that are negative as well as positive. But this is a problem because if x is negative, then the hypotenuse would be negative, and that is contradicting how the hypotenuse is defined. So we need to find an alternative ratio between the hypotenuse and the adjacent side of the triangle that equals x, that does not have x as the hypotenuse and 1 as the adjacent side. And the way we can do this is by recognizing that x is equal to the absolute value of x times the sine of x, where sine is a function that outputs whether 1 if x is positive, -1 if x is negative, and 0 if x is 0. And we can rewrite this as a ratio between the absolute value of x and the sine of x if we recognize that sine of x is equal to 1 over sine of x when x is not equal to 1. X is not equal to 0. And we don't have to we luckily don't have to worry about when x is equal to 0 because arcsecant of x cannot accept 0 as an input. So if we allow absolute value of x to be the hypotenuse and sine of x to be the adjacent side, this is a right triangle that fixes the caveat that the original right triangle had. At this point, if we remember that tangent is a function that takes in an angle in a right triangle and outputs the ratio between the side opposite to the angle and the side adjacent to the angle, we'll see that tangent of the angle in our diagram, which is arcsecant of x, will equal the side opposite to it, which we don't know yet, and we'll have h as a placeholder name for it, divided by the side adjacent to it, which is sine of x. So tangent of arcsecant of x will be equal to h over sine of x. We can find h by using the Pythagorean theorem, where sine of x squared plus h squared is equal to the absolute value of x squared. Now, sine of x squared will always be equal to 1 because x will not be equal to 0, sine of x will always be equal to -1 or 1, and -1 squared is 1, and 1 squared is 1. And the absolute value of x squared is always going to be equal to x squared because x squared is always positive for real x. This leads us to 1 plus h squared is equal to x squared, and solving for h, we see that h could be plus or minus the square root of x squared minus 1. Now we can figure out that we should reject this negative solution because the arcsecant function will always output angles that are between 0 and pi. And if you can visualize this, 0 and pi are angles that always lie in the first and second quadrants. So this height will always be positive. So knowing that we can reject this negative solution, h will be equal to square root of x squared minus 1, which we can plug in here and see that tangent of arcsecant of x will be equal to square root of x squared minus 1 over sine of x. Or, using the property that we described up here, it can be equal to sine of x times the square root of x squared minus 1. Finally, because we found the value for tangent of arcsecant of x, we can plug it into our equation for the derivative of y with respect to x to receive the derivative of y with respect to x is equal to 1 over x times the sine of x times the square root of x squared minus 1. Now, going back to our identity over here, that x is equal to the absolute value of x divided by sine of x, multiplying by the sine of x on both sides, we'll see that the absolute value of x is equal to x times the sine of x. So we can replace this with the absolute value of x, leaving us with the derivative of y with respect to x is equal to 1 over the absolute value of x times the square root of x squared minus 1. Now, we should probably remove this absolute value of x because we still have an integral to solve, and having an absolute value will make the integral quite ugly. And we can do this by pulling out x squared in this other square root, and this will leave us with the absolute value of x times the square root of x squared times the square root of 1 minus 1 over x squared. Now, the square root of x squared is the definition of the absolute value of x, so that will leave us with the absolute value of x squared, which is just x squared. So this will give us the derivative of y with respect to x, and y is equal to arcsecant of x, so we can plug that in, is equal to 1 over x squared times the square root of 1 minus 1 over x squared. Plugging this into our integration by parts result here, we'll receive that the indefinite integral of arcsecant of x over x squared with respect to x is equal to negative arcsecant of x over x plus the indefinite integral of 1 over x to the third times the square root of 1 minus 1 over x squared with respect to x. We'll need to evaluate this indefinite integral now. Although it looks ugly, it can be handled using a relatively simple U-Substitution. We can set u equal to 1 over x squared, and then du will be equal to 2 over x to the third dx. Dividing by 2 on both sides, this will become 1 over 2 du is equal to 1 over x to the third dx. And if we plug this in to the integral, we'll see that it slots in nicely, and the U-Substitution slots in nicely. So then this whole thing would be equal to 1 over 2 times the indefinite integral of 1 over the square root of u, which will be equal to 1 over 2 times the indefinite integral of u to the power of negative 1/2, which will simply be equal to the square root of u, and then plugging u back in, this will be equal to the square root of 1 minus 1 over x squared. And finally, with this result, plugging it back into our integration by parts result, we can see that the indefinite integral of arcsecant of x over x squared with respect to x is equal to negative arcsecant of x over x plus the square root of 1 minus 1 over x squared plus the constant of integration c. Now that we have evaluated this indefinite integral using more traditional techniques, let's see what happens if we use inverse function integration instead. For this example and future examples, I'm going to be a little bit less rigorous and not formally state the domain of the integrand and where it's continuous and invertible as often, like I did in the first example. And I'll do this for the sake of streamlining the integration process. However, if you do want to use inverse function integration, there are two things that you should always check before proceeding. The first thing you should check is where the integrand is invertible on its domain. Ideally, it will be invertible on its entire domain. But sometimes you'll have an integrand that has multiple inverses. And an example of this is the function f of x equals x squared. This is not invertible over its domain negative infinity to infinity because you can have examples like x equal negative 1 and x equals 1, which both output the same y value. And that makes it not invertible. But if you restrict the domain to x solely less than or equal to 0, or x solely greater than or equal to 0, you can have two inverses for this function. And if you set x equal to the inverse of f of u, plug it in and solve for the inverse of f of u, you'll see that the inverse can be either plus or minus the square root of u. And it's the positive square root of u for x greater than or equal to 0, and it's minus the square root of u for x less than or equal to 0. Now, if we could use inverse function integration on a function like this. It is possible. But accounting for multiple inverses can be very tricky. And if you don't handle it with delicacy, you'll receive the wrong answer. Now, I'll give you an example of integrating x squared using inverse function integration at the end to give you a better intuition for what I'm talking about. But if this is the case where the integrand has multiple inverses, I would highly recommend that you try to modify it using something like a U-substitution into a form that only has one inverse, or just use another integration technique altogether. The second thing you should check is if the integrand has a nice inverse. And what I mean by nice is the inverse is able to be expressed using elementary functions, which are functions that are some combination of functions that we're used to seeing, like logarithms, trigonometric functions, polynomials, rational powers, things like that. For example, the inverses of f of x equals x squared are simply just square root of u and negative square root of u. These are elementary. You'll figure out the answer to this question pretty quickly, usually when you try to invert an integrand, because you will, unless you are knowledgeable about some special functions, uh, you probably won't even know how to approach finding the inverse. And if you're in this situation, like in the first case, I highly recommend that you don't try to brute force through it and try to modify it into a new form or just use another integration technique. With all this said, getting back to the indefinite integral that we want to evaluate, I can already immediately tell that this integrand is not going to have a nice inverse. And if you were to plot this as well, uh, it would also have multiple inverses as well. So we're going to do a U-substitution first to get this into a better form. And I can give you, and when you encounter integrands like this, I can give you a hint on what types of U-substitutions you should make. When you are given an integrand that is the product of two functions, one of which being a function that you know how to take the inverse of, and the other being a function that is making it difficult to take the inverse of the previous function. So we know how to take the inverse of arcsecant of x. It's just secant of x. But it being with the product of 1 over x squared makes this much harder to take the inverse of. Probably it would require non-elementary functions. So the U-substitution that we would want to make would remove this extra bit and put everything hopefully inside the arcsecant function. Instead of letting u be equal to something, I'm going to let du be equal to 1 over x squared dx. So when you plug this in, it would just be left with du. Now, integrating this, indefinitely integrating, we'll see that u is equal to negative 1 over x, and solving for x will be equal to negative 1 over u. So plugging this in, we now have a much nicer integrand to take the inverse of, the arcsecant of negative 1 over u. The inverse of arcsecant of negative 1 over u is actually quite simple. It's just negative cosine of u. And now that we know the inverse of the integrand of this indefinite integral, we can rewrite it using the indefinite form of inverse function integration as being equal to u times arcsecant of negative 1 over u minus g of arcsecant of negative 1 over u plus the constant of integration c. G of x is going to be equal to the indefinite integral of the inverse of the integrand which is just negative cosine of u, except I'm rewriting u as x because it's arbitrary at this point. So g of x will be equal to the indefinite integral of negative cosine of x with respect to x, which is just going to be equal to negative sine of x. Plugging g of x back into our equation, we'll see that sine g of arcsecant of negative 1 over u will become sine of arcsecant of negative 1 over u. If we plug back in u equals negative 1 over x and x equals negative 1 over u, we'll receive our final answer. The indefinite integral of arcsecant of x over x squared with respect to x is equal to negative arcsecant of x over x plus sine of arcsecant of x plus c. Using a similar geometric argument to what we did using more traditional techniques, we can rewrite sine of arcsecant of x as the square root of 1 minus 1 over x squared. So this answer is equivalent to what we received using the more traditional techniques. Now that we have evaluated this indefinite integral two different ways, I think there's a strong argument to be made that inverse function integration is a more efficient way of going about this integral than integration by parts, as we did above. My reasoning behind this is that although both methods have a difficult item in them, which is a trig function of arcsecant of x, which can take quite a while to figure out geometrically, inverse function integration produces this item as part of the solution. Meaning we could leave it like this and still have a perfectly acceptable solution to the indefinite integral. While for the integration by parts approach, we had to evaluate tangent of arcsecant of x as part of the process of getting to the solution. We had to do it as opposed to having a choice of whether to simplify it or not. Additionally, in the integration by parts approach, we had to find the derivative of arctangent of arcsecant of x, and we had to deal with absolute values in the integrand and reason through them. So I think that inverse function integration is a more straightforward way to reach the solution. And then if we wish to simplify after that, it's our choice. So far we have done indefinite integrals, so let's spice things up a little bit and do a definite integral for our next example. Let's do the definite integral from x equals 1 to x equals 2 of the square root of x plus 1 over the square root of x plus 1 plus the square root of x minus 1 with respect to x. For the sake of brevity, and not wanting to distract from inverse function integration anymore, I'm going to skip doing this integral and the following integral using more traditional techniques and just jump straight into IFI. Taking a look at the integrand, this doesn't seem like something that we would consider taking the inverse of very often. Compared to the natural log and inverse trig function that we saw in the previous two examples, this doesn't seem to pop out that much that we could consider taking its inverse. However, we might suspect that because there are square roots in here and only powers of 1 inside the square roots, if we take the inverse, we might get some sort of rational function, which might be easier to evaluate. So, and this is part of what I was talking about earlier, that sometimes it's not immediately obvious that you could apply inverse function integration, but it's always worth trying if you think you can do it. We can start taking the inverse of the integrand by setting y equal to it and solving for x. Now, solving for x does take a little bit, but at the end, we receive that it's equal to a rational function just like we suspected at the beginning. If we let f of x be equal to the integrand, and we replace x with the inverse of f of x right here, and y with x, we receive that f of x's inverse is 1 minus 2x plus 2x squared over 2x minus 1. This looks a lot easier to integrate than what we had at the beginning. Using the definite form of inverse function integration, we can set this definite integral equal to 2 times f of 2 minus 1 times f of 1 minus the definite integral of 1 minus 2x plus 2x squared over 2x minus 1 with respect to x from x equals f of 1 to x equals f of 2. We set f of x to be equal to the integrand, and if we plug 1 in here, then we see that f of 1 is equal to 1. And if we plug 2, we'll see that f of 2 is equal to the square root of 3 over the square root of 3 plus 1. Now that we know the values of f of 1 and f of 2, let's work through this definite integral here. This definite integral looks like it would respond well to U-substitution, so we're going to let u equal to 2x minus 1, or x equal to 1/2 times u plus 1. So du will be equal to 2 times dx, and dx will be equal to 1/2 du. Plugging these into the definite integral and changing the bounds of integration by plugging them into our equation for u, the definite integral will become 1/2 times the definite integral from u equals 2 times f of 1 minus 1 to u equals 2 times f of 2 minus 1 of u over 2 plus 1/2 times 1 over u with respect to u. Integrating, this becomes 1/2, the expression 1/2 times u squared over 4 plus 1/2 times the natural log of the absolute value of u, evaluated at 2 times f of 2 minus 1 minus the expression evaluated at 2 times f of 1 minus 1. Plugging this result for this definite integral back into our equation up here, we can see that the definite integral of the square root of x plus 1 over the square root of x plus 1 plus the square root of x minus 1 with respect to x from x equals 1 to x equals 2 will be equal to this expression. Now it's just a matter of plugging in the values that we have for f of 1 and f of 2 and simplifying to get our final answer. After this aforementioned simplifying, utilizing the fact that f of 1 is equal to 1 and f of 2 is equal to the square root of 3 over the square root of 3 plus 1, we receive that the definite integral that we wanted to solve is equal to 5 over 4 minus the square root of 3 over 2 minus 1 over 4 times the natural log of 2 minus the square root of 3. This definite integral was quite algebraically intensive, but the actual integration part of it wasn't too bad, because the inverse of the integrand was simply a rational function, which we could handle using a U-substitution. If you decide to evaluate this definite integral using more traditional integration techniques on your own, you'll find that it can get pretty nasty. The way that I solved it was was manipulating it into a form where I could use a trigonometric substitution, and it involved taking the definite integral of secant cubed at one point, and the integral of secant cubed is quite an infamous integral for its difficulty, so much so that it has its own Wikipedia page. So the fact that we could do this in a completely different way without doing trigonometric substitution, I found it quite satisfying. I'm going to give one more example before I get into an explanation on what happens if you want to use IFI on an integrand that has multiple inverses, and before I give some practice problems for you to work on. This indefinite integral, the indefinite integral of the square root of x squared minus 1 with respect to x, is a fairly common integral. You've probably seen it before. And if we were to approach it using uh, more common techniques, it looks like it's begging for a trigonometric substitution or a hyperbolic trig substitution. But I'm not going to talk about hyperbolic trig substitutions, even though they're probably easier in this case, because they're not too um, often. They're not often taught for some reason, depending on where you're living. And I'll relegate that to be another video in the series. But it looks like we would make a substitution like x equals secant of u, and that would be a good way to solve this, but it will result in you encountering the indefinite integral of secant cubed, which I said in the previous example, that's a infamously difficult integral. So let's see if we can find a way to avoid that using inverse function integration. We're going to start by taking a look at the integrand and seeing if it has a nice inverse. We'll pretty quickly figure out that if we try to invert it, because of the x squared that it has inside of the square root, it can have two potential inverses, plus or minus the square root of x squared plus 1. This is a pretty bad sign, and we could try to accommodate there being two inverses, but we're not going to do that because even if there was only one inverse, the square root of x squared plus 1 is pretty similar to the original integrand that we had. And since we're going to have to integrate this, if we used inverse function integration, it's not really making our lives much easier. We could also try to modify the original integrand using U-Substitution to put it in a more tractable or invertible form. But I don't see any U-Substitution that will really help, at least an obvious one. At this point, we could consider giving up on using inverse function integration, but there is actually one more method we could use to try to change this into a more invertible form that we haven't discussed yet, and that's by using the linearity rules of integrals. This is one of my favorite ways of applying inverse function integration because it really shows how versatile it can be. Start by setting the indefinite integral that you want to solve equal to some function which we'll call I of x. Next, add the indefinite integral of some arbitrary function which I'll call lambda of x with respect to x to both sides. We're not going to set lambda of x equal to anything yet, we're just going to leave it as is. Using the linearity rules of integrals on the right side, we can add these two integrals together to just have the indefinite integral of lambda of x plus the square root of x squared minus 1 with respect to x. Subtract the indefinite integral of lambda of x with respect to x on its own on the left side over to the right side, and we have this equation. I of x is going to be equal to the indefinite integral of lambda of x plus the square root of x squared minus 1 with respect to x minus the indefinite integral of lambda of x with respect to x. And what this tells us is that or what we can do is, if we can find a function, lambda of x, that makes this integrand more invertible, and so we can then solve this using inverse function integration, and if lambda of x, once we set it, is also easy to integrate on its own, we can then solve for I of x. To continue, we're going to start finding the inverse of this integrand. And this will give us hints at what we should set lambda of x to be to make it more invertible. Let's set y equal to lambda of x plus the square root of x squared minus 1, and subtract lambda of x from both sides, and square both sides to receive y squared minus 2 times y times lambda of x plus lambda of x squared equals x squared minus 1. At this point, we can set lambda of x to be x. And if we do this, we could cancel the x squared from both sides and just have x here. This would be a very good substitution for what lambda of x should be, because this x squared in the original integrand, when we tried to invert it, caused there to be two inverses. So if we set lambda of x equal to x, it will get rid of that x squared, leaving us with just one x, causing there to be only one inverse. When we make this substitution and solve for x, we'll see that x is equal to 1 over 2 times y plus 1 over 2 times 1 over y. And then if we allow f of x to be equal to this integrand, then its inverse will be 1 over 2 times x plus 1 over 2 times 1 over x. If we use inverse function integration then on this indefinite integral, knowing its inverse will be this, we can easily find the indefinite integral, because this inverse is not too bad to integrate. Also, when we set lambda of x equal to x, we do also have to take its indefinite integral, but the indefinite integral of x with respect to x is just 1/2 x squared. So we have effectively reduced this problem into a much simpler form. Using the indefinite form of inverse function integration on this indefinite integral, where lambda of x is equal to x, we can see that it becomes x times, in parentheses, x plus the square root of x squared minus 1 minus g of x plus the square root of x squared minus 1 plus the constant of integration c. And g of x is just equal to the indefinite integral of 1/2 times x plus 1/2 times 1 over x with respect to x. Integrating this just becomes 1 over 4 times x squared plus 1/2 times the natural log of the absolute value of x. Plugging g of x back into the equation and simplifying, we'll receive that the indefinite integral of x plus the square root of x squared minus 1 with respect to x is equal to 1/2 x squared plus 1/2 times x times the square root of x squared minus 1 plus 1/4 minus 1/2 times the natural log of the absolute value of x plus the square root of x squared minus 1. Now, I'm dropping the constant of integration here because we'll add it at the end of this, since this is only one part of solving for I of x. Plugging our result for this indefinite integral into our equation for I of x and simplifying, by combining 1 over 4 with the constant c, because they're both constants, we can just rewrite them as a new constant. And after indefinitely integrating x, we get our final answer that the indefinite integral of the square root of x squared minus 1 with respect to x is equal to 1/2 times x times the square root of x squared minus 1 minus 1/2 times the natural log of the absolute value of x plus the square root of x squared minus 1 plus the constant of integration c. For an integral that would have normally required trigonometric substitution, I think what we did is a pretty nice and fairly quick alternative path to reach the solution. Now that we've done this, I'm going to go into one more example. And this example is going to be what happens, or what should we do, if we want to find the definite or definite integral of a function using inverse function integration that has multiple inverses. To show this, I'm going to choose a simple function to integrate, namely x squared. I'm going to let f of x be equal to x squared, and we can see that f of x will have two inverses. For x greater than or equal to 0, f of x will invert into the square root of x, which I'm denoting as the positive inverse of f. And for x less than or equal to 0, f of x inverts into the negative square root of x, which I'm going to denote as the negative inverse of f of x. To visualize this, I have two graphs. The first graph is simply of f of x equals x squared. And we can see that for all real x, it is not invertible, because it will have the same y value for x values that have the same magnitude. But if we split the graph into two different sections of its domain, which is for x less than or equal to 0 or x greater than or equal to 0, these sections are invertible because they don't have the same y value twice. The yellow section, which is for x greater than or equal to 0, will invert into the positive square root. And the cyan section will invert into the negative square root. If we don't split up the domain of f of x equals x squared to invert it, then its inverse will not be a function, because it will give two y values for one x value, or it will fail the vertical line test. So we need to split it into two different inverses. Keeping this in mind, let's do the definite integral of x squared with respect to x from x equals -1 to x equals 1. Now immediately there's a problem, because x squared is not invertible over the interval -1 to 1. What we can do to rectify this, though, is to split the definite integral into two definite integrals. The first being over a region where x squared is invertible, and the second being over a region where x squared is invertible. X squared is invertible over the interval -1 to 0. Its inverse there is the negative square root of x, and it is invertible over 0 to 1, and its inverse there is the square root of x. So we can use the definite form of inverse function integration on these two definite integrals separately. If we do this, we're going to first do this definite integral. The definite integral of x squared with respect to x from x equals -1 to 0 using the definite form of inverse function integration will be 0 times 0 squared, which is just 0, minus -1 times -1 squared, minus the definite integral from x equals -1 squared to 0 squared of its inverse over this interval, which is the negative square root of x with respect to x. Simplifying, this is just equal to 1 plus the definite integral of the square root of x with respect to x from x equals 1 to 0. Integrating this and simplifying, this is just 1/3. We can do a similar process for this definite integral to show that the definite integral of x squared with respect to x from x equals 0 to x equals 1 is going to be equal to 1 times 1 squared minus 0 times 0 squared minus the definite integral from x equals 0 squared to x equals 1 squared of x squared's inverse over this interval, which is the square root of x. And simplifying, integrating and simplifying, this is equal to 1/3 as well. So this definite integral will be equal to 1/3 plus 1/3 to just be 2/3. We can check this by integrating more traditionally, where the definite integral of x squared from x equals -1 to x equals 1 will be equal to 1/3 times x to the third evaluated at 1 minus it evaluated at -1, which is just 2/3. So these are both the same. So this is how you account for multiple inverses, or this is an example of how you can account for multiple inverses for definite integrals. To use inverse function integration on an indefinite integral with an integrand that has multiple inverses, it's a somewhat similar process. You will need to use the indefinite form of inverse function integration on the indefinite integral for as many inverses as the integrand has. And at the end, after you've computed all of these indefinite integrals, you will hopefully be able to find a way to combine all the antiderivatives that you have now into one antiderivative. To give an example of what I'm talking about, I'm going to do the indefinite integral of x squared with respect to x. As we've previously discussed, f of x equals x squared has two inverses. The square root of x for x greater than or equal to 0, and the negative square root of x for x less than or equal to 0. We will need to use the indefinite form of inverse function integration for each of these inverses. For the positive inverse, or the square root of x, we're going to say that the indefinite integral of x squared with respect to x is equal to, through the indefinite form of inverse function integration, x times x squared minus g of x squared plus a constant of integration c. Now I'm going to call this constant of integration c1 because we're going to have 2 in the end, where g of x is equal to the indefinite integral of the positive inverse. So the indefinite integral of the square root of x with respect to x, which is just 2/3 times x to the power of 3/2. Plugging this in, this will all equal x to the third minus 2/3 times x squared to the power of 3/2, plus the constant of integration. Now, don't fall into the trap of just multiplying these together and saying that this is equal to x to the third, because of the square root that's in here, the x squared and the square root will combine to produce the absolute value of x, and so the final answer that we're going to get for x greater than or equal to 0 is that the indefinite integral is of x squared with respect to x is equal to x to the third minus 2 over 3 times the absolute value of x to the third plus the constant of integration c1. And this is for x greater than or equal to 0. If we do a similar process for x less than or equal to 0, where the inverse is the negative square root of x, we will get an answer that is almost the same, but it is a little bit different. And that's that the indefinite integral of x squared with respect to x is equal to x to the third plus, instead of minus, 2 over 3 times the absolute value of x to the third plus the constant of integration, which I'll call c2, for x less than or equal to 0. We now have two antiderivatives for the indefinite integral of x squared with respect to x, one for x greater than or equal to 0, and the other for x less than or equal to 0. We should now try to combine these two antiderivatives to make one antiderivative that can accept any x value on the real number line. In order to do this, we're going to need to make sure that these antiderivatives are continuous with each other. At the one x value that they both have in their domain, which is x equals 0, they're probably discontinuous because they have two different constants of integration. If we set them equal to each other at x equals 0, we can see that that necessitates c1 to equal c2. If we set c1 equal to c2 equal to just some constant of integration c, we can rewrite the indefinite integral of x squared with respect to x equal to x to the third minus 2 over 3 times the absolute value of x to the third plus c for x greater than or equal to 0, and x to the third plus 2 over 3 times the absolute value of x to the third plus c for x less than or equal to 0. And these antiderivatives are now continuous with each other because they have the same value at x equals 0. Now, because these two antiderivatives are only different from each other by the sign before the 2 over 3 now, we can further combine them into one antiderivative by recognizing that for x greater than or equal to 0, we could say that because x is positive, or 0, it's not contributing to flipping this negative sign. And when x is less than or equal to 0, or x is negative or 0, we can say that it is contributing to flipping the negative sign, and it flips it into a positive sign by multiplying into it. If we view it in this way, we can say that there is a sine function right next to the 2 over 3. So when x is less than or equal to 0, or when x is less than 0, this will flip to a positive sign. And if it's greater than 0, it will stay a negative sign. We can then recognize that the sine function, because it only outputs 1, -1, or 0, it is equal to the sine function to the third, because 1 to the power of 3 is 1, -1 to the power of 3 is -1, and 0 to the power of 3 is 0. Using this, we can combine sine of x and the absolute value of x to the power of 3 into sine of x times the absolute value of 3 to the power of 3. And then we can further recognize that x is equal to the absolute value of x times the sine of x. And if we plug this in and simplify, we can get that our final answer for all x, the antiderivative of the indefinite integral of x squared with respect to x for all x on the real number line is 1 over 3 times x to the third plus a constant of integration c. And we can verify this is correct quite easily just by looking at the indefinite integral and solving it using more traditional techniques by just adding 1 and then dividing by 3. Now that we've done an example of using inverse function integration on a definite and indefinite integral with an integrand that has multiple inverses, you can probably understand why I said earlier that it's likely not useful to use inverse function integration in these cases, because having to split an integral into as many integrals as the integrand has inverses can greatly complicate the problem. We just saw how it could take a simple indefinite integral that could take only one line using more traditional techniques and turn it into just a massive mess. I mean, at the end of this mess, we got the right answer, but it's certainly a roundabout way of doing it. If you know of any special edge cases where inverse function integration, despite the integrand having multiple inverses, is still very useful, let me know. I think that'll be really interesting to look at. We've now reached the part of the video where I've run out of examples that I wanted to show you, and I don't actually have much more to say. If you've made it this far, I greatly appreciate you watching and sticking around. I hope you've learned something new. I hope you had fun. Hope you found the topic that we talked about interesting. I realize that at some parts in the video I was probably a little slow and perhaps overly rigorous. I'm still not too sure how to make YouTube videos, and my public speaking skills aren't too good, but I'm hoping to get better just by making more videos. I'm going to leave you with some practice problems for you to further hone in your inverse function integration skills and to try to train you to recognize where you can use it more in practice. I'll make a video after this one going over these practice problems to show you how I would approach them. And with that all said, once again, thank you very much for watching. I greatly appreciate it. And I'll see you guys next time.